Hello. Good morning, sir. हाँ शुरू कीजिए. Thank you, madam. Nice introduction. Now we are going to start directly lecture in the area of custom power devices and its application in distributed power generation system. In this case, we will discuss about the okay. Now all are able to see the slides. Hello. Hello. You are able to see the slides. Oh, okay. Okay. Now we are going to discuss about the custom power devices design, some basic control, and its application in. We will take one application only that is based on the wind power. Inside of that, we are going to discuss about the induction generator and synchronous generator. Okay. First, we are going to start inside of custom power devices. We are going to start this statecom. This statecom means how we can design, what is a circuit, what are the component, and how we can utilize for solving current-based power quality problems. So again, we can see in power quality, maybe we can classify in two categories in the area of compensation. First one may be current-based power quality problem. Second may be voltage-based power quality problem. We will discuss both. Current-based power quality problem, we are going to discuss about the shunt-connected distribution static compensator. Okay. Simply we can say it is the one member of the custom power device. It can mitigate or compensate unbalance distortion in case of power factor correction mode and ZVR mode created by the linear or non-linear load. Linear load means maybe we can say inductive loads. Up to some level we can say linear, and also non-linear means all the switching devices, all the means rectifier, all the power electronics converters. Maybe you can say machines also. Maybe you can say up to some level, and also maybe we can say all these drives also. Maybe we can say it is operated in generally PWM switching only because we are going to take switching frequency near to 5 kilohertz, not more than 10 kilohertz, because we are going to deal medium switching frequency range. So main advantage is this will give dynamic compensation. Means dynamically we can compensate the whatever problems are coming. Maybe reactive power, maybe harmonics, maybe unbalancing, load side unbalancing means supply we are going to make balance, maybe neutral current compensation. Means we can compensate the neutral current if we have 4-wire system. And second one, capacity of the tangent overload even at reduced voltage level. At any voltage level, the whole system will work. If we have designed of some highest voltage, the lower voltage also will work. 10 volt, 50 volt, 200 volt, 300 volt, 415 volt, and any level we can get the compensation. Means that one also maybe we can consider as a beauty of the power electronics. Means suppose one converter we have designed for 415 volt, some ampere, maybe 100 ampere. So that will also work for 10 volt, 1 ampere, 2 volt, 5 ampere. Any condition that will work. Then this statecom is going to operate two mode. One is the power factor correction mode, and second one the voltage regulation mode. But only problem with voltage regulation mode is there. We are going to observe slightly leading power factor. That is the maybe we can say this is the disadvantage. But up to some level 5 volt, 10 volt we can compensate. No problem here. Means we can maintain the rated required voltage, whatever voltage we want. But if we are going to run system in ZVR mode, then we are not able to maintain the PFC. Means we are not able to maintain the angle between current and voltage near to 0 or equal to 0, you can say here. Okay. Means if you want to maintain the PFC mode, then you can PFC. If you want to operate only PFC mode, so according to that one, you can design the control logic. If you want to maintain ZVR mode, According to that one, we can design we can add some more extra control circuit. That is meaning. Okay, at a time, only one mode is going to operate, maybe PFC mode or maybe ZVR mode. Okay. In case of ZVR mode, what we are going to do? We are going to compensate the whatever voltage that we are going to observe due to source impedance or due to loading. Suppose we are going to see in our home also, maybe our college also. Suppose we have bus bar. In that we have a voltmeter, ammeter, everything we have. In that case, if morning, you can say the morning maybe 10 o'clock, maybe 8 o'clock, if we are going to see our voltage level is 415 volt or 440 volt, currently maybe 10 ampere. After afternoon, maybe you can say 2 o'clock, maybe 12 o'clock, that current is going to increase maybe 20 or 25 ampere, and voltage is going to reduce maybe 410 or 405. But if we are able to maintain that voltage near to 415 only, and whatever current we want to take, in that case, we should compensate the voltage also. So by this device, we can compensate, but problem is we are going to observe slightly leading power factor. That is disadvantage. Okay, performance and effective utilization, how we can observe this one? That depend upon the control. Whatever control you have used for generation of reference current, and how you are going to control. Maybe that can control, maybe in that can control. Any type means we can control two types. One is that directly you can compensate the required current, or maybe indirectly you can generate the compensating current. In case of that can control, you can generate the reference current. In case of that can control, directly we can compensate the we can generate the required compensating current. Okay, switching scheme also we need to design switching scheme also. Also performance depend upon the design of power circuit element. Means whatever element you have used, inductor, capacitor, RC filter, voltage source converter, means performance depend upon the tuning of these element also. So you can see here many controller are there, and topology also there. Then depend upon the application, depend upon the load condition, we can use. So selection of any control, maybe PFC mode, maybe ZVR mode, depend upon the time required for estimation of active and reactive current component and reference current. Means how much time is required to estimate the active and reactive component of the load current, you can see, or maybe whatever load we have connected, in that how much they are going to demand the active and reactive current, and based on that one we can generate the required reference current. Use of intermediate filter in control algorithm means inside of control algorithm, generally we are going to convert AC to average value. So in that case, we need to filter out the whatever ripple component there, whatever offsetting component are there, those we should filter out. Independent control in all three phases, if possible, we can control. We need to control independent all phases, one phase, two phase, three phase. So generally, we have three phase system. We should control all three phases independent nature. So for that case, for this application, maybe we can use single phase peaking three phase control. We can use in PFC and ZVR mode. So what is the advantage? Advantage of control is high convergence rate, high convergence speed we need. Independent control in all three phases. The structure of control is based on the basic arithmetic operation. Due to this, its implementation in software and hardware is very simple. Whatever control we are going to discuss, that is based on the simple arithmetic operation only. Means simply mathematical analysis, simply mathematical calculation based.
Hello.
Due to this, hello.
Sorry.
Hello.
Testing.
Due to this region, its implementation in software and hardware is somewhat simple. Software means you can use MATLAB. Hardware maybe you can use any DSP processor. You can write the code, maybe C, maybe MATLAB code. MATLAB simulation also you can do, depend upon the facility inside the processor. Or maybe also you can use any microcontroller, just 8051, or maybe any STM advanced 32 or 64-bit microcontrollers. Anything we can use here. Means if we are going to work for such application only, then maybe we can use some advanced control, because in that case we need within less time we want highest output. But if we want to make for commercial application, then you can within 1 month, 2 months, 3 months, 4 months you can test, maybe 6 months also you can test. You can use any low cost processor so that we can reduce the cost also. After that, if we have made once we have developed everything code and everything we have developed setup, that one commercially we can produce, commercially we can make in production. Okay, in that case we don't require any research work. Only once we have done everything with the same circuit, you can reproduce maybe 1,000 times. That is meaning. Any question till now? Okay, if we are going to use only for research application, if we are going to do research in this area, then we can use for high-end processor, so that we can capture the whatever problems are coming, whatever shortcomings are there for control or maybe topology. In that case, we need high-end processor so that we can capture the response within micro or milli or maybe nanosecond also. But after implementing everything, if whole technology is going to work very well, then you can suggest for commercial application. In that case, we can change the processor. We can set any suitable processor for commercial application. That is point. So for that one, we have taken one topology, very basic topology. Here we have taken one 3-phase 3-wire system, 3-phase 4-wire system, and fourth wire we have connected to non-linear load. Assume that we have 3 single-phase load, 3 single-phase rectifier, and output side of rectifier is RL load. Okay. Again, in this whole circuit, what are the components? First component is only converter, voltage source converter, with DC link, control algorithm. Also, we have a ripple field RNC. Apart from that, we have one, two, three, four. We have fourth element is the star data transformer. Means by a star data transformer, we want to compensate the neutral current. Means what generally always means frequency of neutral current is 150 Hz. That is third harmonic only. So for third harmonic, if we are going to create delta in secondary side, the third harmonic will circulate inside the delta only. Okay. If you want to make in this way, if you want to neutralize the effect of that one, you can change the transformer connection. You can do any other connection. Okay. Here again, this is a voltage source converter, and we have a RC filter. Then between converter and PCC, we have an interface inductor. Your first requirement, first and most effective requirement is you should maintain DC link voltage at least peak value of line to line voltage. This is the main requirement. Our main requirement is if converter is going to work as a compensator, you should maintain DC bus voltage VDC at least peak value of line to line voltage. From that point, our converter is going to work as a compensator. For sufficient operation, you can use formula. Okay, so 1.65 times that VDC or V line to line. That one you can maintain. Okay. Again, to get the operation of VSC, to get the to operate the VSC as a compensator, you can maintain DC bus voltage more than line to line, more than peak value of line to line voltage. Line to line means VSA, VAB, voltage between line 1 and line B, line A and line B. Whatever name you can use, VAB and VBA, or VSA and VSB. Line to line means you can maintain that DC link voltage more than VAB, more than peak value of VAB. AB means line to line voltage. Okay. After that, directly we cannot connect this compensator to line. Okay. Between that one, you can get the voltage drop. Okay. If line voltage more than converter voltage, converter output voltage. Again, I will tell here. If line voltage VABC, those voltage are more than converter output voltage, converter output AC voltage, then power is going to flow line to converter. Second case, if converter voltage more than line voltage, power is going to flow from converter to line. Those operations we can manage by this inductor. Again, new point, Generally, always we are going to connect one RC filter. RC filter means one passive filter, so that we can reduce the switching frequency, reduce the noise generated by the switching frequency on line voltage. By RC filter, you can reduce noise superimposed in the line voltage. This is the main thing. By RC filter, we can, by RC filter is going to provide one low impedance path to flow the switching noise. Otherwise, whatever switching noise we are going to get from converter, na, all those noise going to superimpose with line voltage. Again, this is one theory. Second theory is, again I will tell one new thing, maybe not new thing, just only our understanding only. Suppose our load have 25% distortion in current, and line to line, maybe in PCC voltage we have a 3% distortion without compensation. Without compensation, line in that load current we have 25% distortion without compensation. Okay, and voltage we have 3%. After compensation, if we don't have a RC filter, in that case you are going to observe, in current you are going to observe 3% distortion, and voltage you are going to observe 25% distortion. Not 25, maybe 25.5, maybe 24, near to 25. Means with the help of compensator, we have shifted the current harmonic to voltage harmonics. This is meaning. With the help of voltage source converter, we have compensated current harmonic to voltage harmonics. Just we are going to shift, but we are telling we have compensated. Okay. This means we have two theory here. One is a compensation. If we are going to see in practical way, then we have shifted the distortion, and whatever distortion we have observed in line voltage, though easily we can ground through the RC filter. RC filter means this filter is basically based on the resistance and capacitor. The resistance is fixed value, maybe 5 ohm, 10 ohm, 20 ohm, any value you can take depending upon your whole circuit. And capacitor maybe also you can take maybe 10 microfarad, 20 microfarad, depending upon the whatever element you have connected and their impedance and tuned value of tuned value of capacitor. Let us we have taken 10 microfarad. Now find out the impedance of capacitor. How much? Suppose we have 10 microfarad capacitor. So what is the impedance? What is the reactance? Anyone can tell? Hello? Anyone can tell what is the reactance? If frequency is 50 kilohertz, or maybe you can say R equal to 5 ohm, frequency 50 hertz, capacitor is 10 microfarad. So what is the value of this RC filter impedance per phase? Anyone can tell? Hello? 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 Anyone? Hello? Okay. Suppose you can find out the R plus JXC. A value of XC how much? 1 by 2 FC. If F is 50 hertz, you can find out the value of XC. You can find out the impedance, total impedance. If frequency is going to increase, then your reactance is going to decrease continuously. If frequency is going to increase, maybe 50 has some value, 100 has some different value, 500 has some other value, 5 kilohertz some other value, means this filter is going to create the effective performance after half of the switching frequency. Okay? Clear now? Means after half of the switching frequency, this one is going to provide one effective low impedance path to flow the whatever switching distortion we have observed in PCC voltage. Okay. One more thing. One main thing is there. Always we are telling we should take the voltage source converter, and we should design the capacitor in DC side. Also, we should design the value of inductors, capacitor voltage, switch voltage rating, switch current ratings. How we can decide? For one case, we will take something. In case of second element DVR is there, then those also we can read. After that, we have application of these in wind farms. हेलो मैं फोन करता हूँ अभी है 12 बजे तक हाँ मैं डिपार्टमेंट में 12 बजे तक फोन करता हूँ अभी क्लास है हेलो suppose assume that we have 35 kVA load. Okay, assume that we have load rating is 35 kVA, power factor is 0.8. Okay, the power factor is 0.8, that means you can find out the active power and reactive power. Okay, so for active power how we can multiply 0.8, you can multiply. For reactive power you can multiply by 0.6. Whatever value is coming, that value is the required, that value is the reactive power required by the load. So 35 into 0.6 how much? Near to 21. 21, then maybe also you can take 10 to 20% extra you can take. So finally, we are going to take 25 kVA voltage source converter. Means how we have decided that I want to take. First you can calculate what a problem you are going to solve by this converter. Assume that we have only first case only assume that we have only reactive power problems. So whatever reactive power is there, that reactive power you can calculate, you can take 20% extra. And that extra value depend upon your budget. Second case, suppose you are going to solve two problems. That we don't know if that problem will come same time or at different time. If those problems are coming same time, you can calculate the rating of the reactive power. Also, you can calculate the rating of the harmonic power. Both you can add. If we are thinking maybe harmonic will come sometime, that with that time maybe we don't have a problem, we don't have a requirement of reactive power whole 100%. In that time, maybe you can take whatever highest rating is there. Only based on the reactive power compensation, you can design the what you can design. You can design the voltage source converter. Third case, maybe you have unbalancing also. All three problem coming at a time only. Reactive power plus harmonic plus unbalancing. All three ratings you can calculate, you can add, and based on that one, you can design the voltage source converter kVA rating. Okay. Next case, suppose we have all four columns, and we are going to compensate using 4 leg converters. In those cases, you can add harmonic power, reactive power, unbalanced power, and power requirement due to for compensation of neutral current. All four components you can add, then you can take 10% extra. Based on that one, again you can make a round figure, and also you can see the market condition. If manufacturer is going to manufacture maybe 90, suppose value coming 80 kVA. If a manufacturer they have 100 kVA converter, to design the 80 kVA, that again that need some special design. Special design converter may be somewhat costly. Then you can take only 100 kVA converter, no problem, because that is commercial design only. Next case, how we can design, how we can select DC bus voltage. You can use 2√2 V line to line divided by √3 formula. Based on that one, whatever value is coming, you can take round figure. Guideline is you should maintain DC bus voltage at least peak value of line to line voltage. From that point, converter is going to work as a compensator. Next case, how we can design capacitor? The rough guideline is for each 5 kVA, you can take 2000 microfarad. And also you can design this one based on the 1 by 2 CV square equal to 3 VI into T. Based on that one, also you can design the value of DC link capacitor. Means DC power equal to AC power. Here value of alpha is the overloading, T is the time requirement for recover the DC bus voltage during dynamics. Suppose our load is unbalanced, our system is unbalanced, that time how much time is required to recover the DC bus voltage. This value generally we are going to take not more than 500 microsecond. Generally 200 to 500 any value we can take. Okay. And also during dynamics, we are not going to observe 100% power fluctuations. Then maybe you can take K equal to 3 to 20%. Based on that one, we can calculate. After calculation, maybe we get some value. We have got 8432.40 microfarad. Round figure you can take 10,000. Also, you can design DC bus voltage based on the DC size calculation. So the formula is CDC equal to ID divided by 2 pi 2 mega into VDC RP. VDC RP, okay. RP is the maximum allowed ripple in the DC bus voltage. Omega is the 2 pi into F. F is the 50 hertz. ID, how we can find out the ID? DC kVA divided by DC bus voltage. So we have how much we have taken? 25 kVA converter we have taken. DC bus voltage 700 you have taken. 35.71 will come. Also you can see how much ripple we are going to allow inside the DC bus voltage. Assume that DC ripple on the DC bus voltage 0.5 to 1% only. So maybe 5 volt you can take. Based on that one, you can calculate the DC bus voltage. You are going to get near to 10,500. So you can take only 10,000 only. Because 10,500 we will not get. Maybe 10,000, maybe 12,000, maybe 5,000. In that way, manufacturer will develop the capacitors. Value of inductor also you can design based on this formula. Root 3 EMA VDC 12 into alpha switching frequency and that ripple on the compensating voltage. This one already we have discussed. What is the role of ripple filter in this shunt active filter? You can say how we can design switch that voltage switch. You can take DC bus voltage and 10 to 20% extra you can take. Because during overshoot, maybe DC bus voltage going to increase up to 10%. But that is the maybe more than that will go. So assume that our DC link voltage is 700. You can take 70% extra. So 770 again point is there. Cost of 770 and cost of 1000 for DC IGBT nearby same only. So maybe you can take higher end IGBT. Maybe you get 1,000, maybe 1,500. Because cost variation very less. 1000 volt and 800 volt DC 800 volt IGBT. Maybe we will not get 800 volt IGBT. Maybe we will get only 1000 volt IGBT. How we can decide the current rating? So you can take 1.25 peak value of distant current and value of allow ripple on that. So whatever converter is going to supply, the current, that peak value plus percentage ripple on that current. You can take that. Based on that one, you can select the IGBTs. Here in our application, we have selected SKM 200 GB 12 volt. 1200 volt and 200 ampere. You can see inside of this IGBT module itself 200 volt, 1200 volt, 200 ampere. This is one basic control. This one we want to discuss, and also we will show the result of this one. Okay. This is very basic control only. all the books, all the places they have given this type of thing. So in this, using this one, we want to generate the required reference current, and we want to control whole converter based on the indirect current control thing. So first and most requirement is, if we are going to run the whole system in PFC mode, only you can use DC bus loop only. Upper section you can use. If we are going to use at voltage regulation mode, you can use VT as well as the DC link mode both. Mean in case of voltage regulation mode, you can use two PI. One PI used for the one PI used for maintaining the DC bus voltage. Second one is used for to maintain the VT, mean maintain the PCC voltage. Okay. To maintain the PCC voltage, one PI you can use. To maintain DC bus voltage, another PI you can use. But whole system, first you can run in PFC mode. After that, you can shift to ZBR mode. Means how we can switch on the system. First, you can run the whole system in PFC mode. You can maintain DC bus voltage. Second case, you can put one step PI loop and set the terminal voltage, put some reference value, compare. After comparing, you have error. That error you can give to PI controller, tune the value of KPKI. How we should know value of PI KPKI are tuned? In that case, you are going to get output of PI minimum constant DC. And in that condition, you are able to maintain VT equal to VT dash. If we have VT equal to VT dash and output of PI is minimum constant DC, then you can say our PI is tuned. That value you can add with load reactive component. Load reactive component. Same way, in case of DC link, first you can sense the DC bus voltage by some sensor. Second case, you can put one reference, this much voltage we want to maintain. Both you can subtract. Reference always you can put positive, and DC can sense DC bus voltage, you can put negative. After that, whatever value is coming, whatever output is coming, that output you can process through PI controller. Put value of KP, put the value of KI, tune continuously up maybe 1 hour, 2 hour, 3 hour, maybe 1 month also. Depend upon the experience in tuning of PI. This is one case. Second case, maybe you can use any PI tuning techniques. And after tuning the value of PI controller, how we can identify our PI tuned or not tuned? In that, if PI is tuned, you are going to get output of PI controller minimum constant DC. You are going to get output of PI controller minimum constant DC. Then at that also we are going to consider last component of voltage source converter. Also maybe you can consider loss component of voltage source converter. Both you can add. After adding, you can calculate the value of active component of reference supply current. Active power component of current in reference supply, for reference supply can you can say. In next case, output of PI controller, maybe you can use QC. Generally, output of PI controller is only signal. But based on the other component, maybe you can consider as a power, maybe current, maybe voltage. Okay, but basically this is the one signal only. Okay, so depend upon the other component, you can consider output of PI, maybe power, maybe current, maybe voltage. Okay, so in case of VT loop, again you can QLA plus QQC. Both you can add. After adding, again you can calculate the reference reactive current, or reactive component of the reference current, you can say. Reactive component of reference current. After getting active and reactive, you can add And after adding, you have a ISA star, ISB star, ISC star. These are the reference current. Again, we are going to tell our supply current. That then a supply current is distorted and unbalanced due to nonlinear load. And from this controller, we have generated pure sinusoidal reference supply current. One is sine wave, second is distorted wave. And we are going to force our to supply, that controller is going to force the supply to follow their nature. This controller is going to force the supply, they should follow reference supply current nature only. It means reference is always positive. Reference is always supreme only. Reference is always positive. Reference minus supply, you will get error. That error you can pass through maybe on PI controller also. After passing the PI controller, you can compare with triangular wave, or maybe you can use statistical controller. If we are going to use triangular wave, you can select particular carrier frequency, maybe 5 kilohertz, maybe 10 kilohertz, maybe 1 kilohertz. After comparing, you have a gauge signal, or whatever gauge signal is coming, you can give respective phase IGBT, respective phase voltage source converter connected in respective phase first IGBT. Again, whatever error is coming, that error you can generate the gauge signal. That gauge signal you can give respective phase leg, whatever leg we have connected voltage source converter, in that leg first IGBT. Okay. Suppose we have taken error from phase A. So in phase A, whatever leg is connected, that leg first IGBT. And same gauge signal you can pass through one NOT logic, and that after passing through NOT logic, whatever gauge signal is coming, that gauge signal you can give lower IGBT. In that way, we can generate the gate pulses and we can switch on the voltage source converter. Whole theory again we will tell one by one. So first thing is, whatever supply voltage and supply current you have sense. Now supply here generally load is supply voltage and this is load current. Whatever current you have sense, first you can take directly, I consider as a V alpha ABC, V alpha, V beta, V alpha A, alpha B, alpha C, V beta A, beta B, beta C. Okay, beta means 90 degree leading. Whatever voltage there, in that voltage you can make 90 degree lead. Same as current also. So you can say load current here, na supply. Initial case supply and load same thing only. So generally we are going to take only load current. One component directly you can give inside the box, and second component you can shift 90 degree. 90 degree shifted component you can consider as a I beta. Directly whatever component directly you have given, that one you can consider as a I alpha. Then you will find out the powers. Generally power is the calculation of current and voltage. Power is the multiplication of current and voltage. After multiplication, if we are going to multiply 2 sine wave or 2 square wave or 2 any AC wave, you will get one average value. A second also you are going to get the offsetting component. To remove the offsetting component from that whole, to remove the offsetting component, we need to connect low pass filter, so that we have only average power. The average power, with the help of average power, you can find out the total value of total reactive power. Then you can put 1/3, so that we have a load balancing phenomena in our system. Okay. If we are not going to put 1/3, we are not able to get a load balancing phenomena. Now you can see how we have converted. Just we have converted whatever ABC are there, in that alpha, whatever alpha are there, those alpha we have converted to beta. After safety 90 degree. Between current and voltage also we have a pi L phase delay. Okay. Then you can find out the power. How we can find out the power? Simply you can multiply V alpha A, I alpha A, V beta A, I beta A. For phase A, phase B, phase C. Then you can find out the average power. PLA equal to phase A power, phase B power, phase C power divided by 3. Then whatever value is coming, that value you can add with PI controller, and also you can find out the amplitude of VT voltage, PCC voltage. Similar way you can find out the reactive component. In case of reactive component, formula is V alpha I beta minus I beta I alpha. For phase A, you can put phase A all the places. For phase B, you can put phase B other places. For phase C, you can put phase C. Then you can take average, find out the formula for, find out the expression for output of PI controller. Now you can find out total load, total instantaneous value of load reactive power component of reference source current. That is QT equal to QLA plus QC. Then find out using this formula, find out the value of reference supply current. ISC star, ISB star, ISC star. Here we have used 10 kHz switching frequency. Then based on that one, you can generate the required gas signal. These are our simulation result. Simulation, whatever data we have taken, these are implementation data. In simulation, you can see after compensation how much distortion we are going to see in supply voltage. 2.64 current to 3.8, but in load side how much? 40%. Up to from 40% to 3% we have maintained. Okay. Same in ZVR mode, 40.51% we have a distortion in the load side. After compensation, in current how much? 3.83. Voltage how much? 2.50. Okay. Now you can see the angle between current and voltage. See the angle? See the figure 4.4A and 4B. See the figure 4A and 4B. See the nature of supply current slightly leading compared to voltage. Very minor value because we have only here 27 ampere current. Okay. Also we have done of course the whole work in simulation only. Do that one maybe we are not able to see properly, but we have very small power, small angle between current and voltage. Current is going to lead. Same thing also you can see in experimental result. In case of PFC mode, assume that we have tested whole system in 180 volt or 160 volt. After compensation, we are going to observe supply voltage distortion how much? Less than 5%. But load distortion how much? 32%. Phase A, 37% phase B, 33% phase C. Also you can see nature of supply currents. Also you can see the figure 5 P and Q. See the figure 5 P and Q. In that you can see the wave shape of neutral current. One is a load neutral, second one is supply neutral. Both are equal and opposite. One is the not supply neutral, one is load neutral, a second one the you can see here. One is load neutral, second one transformer neutral. Okay. So transformer neutral and load neutral both are equal and opposite. Okay. If a load and transformer neutral both are equal and opposite, it means our supply neutral current is going to become 0. Near to 0 you can say. Maybe 1 ampere, 0.5 ampere, maybe some value there. Here our load neutral how much? 5.42. Supply neutral how much? 5.43. But that depends upon the supply, देखो load neutral 5.42, transformer neutral 5.43. This one, suppose we don't have a sufficient rating transformer, then maybe based on their capacity, transformer will give current. Okay. After current also you can see supply voltage distortion. Supply, we should also maintain supply voltage distortion near to how much? Less than 5, na? According to IEEE 519, maybe you can consider 2014, 2014, IEEE 519. Also, you can see how our system is, how is this voltage source converter is going to maintain load balancing. See, our phase A load, phase B load, phase C load. One phase load is 0. Still, we are going to observe balance sinusoidal current from supply side. Means our supply should not going to become unbalanced. Okay. To maintain the figure A, B, and C, what type of current we need from converter? See the figure G, H, and I. G, H, and I. Current figure 6, G, H, and I. With the help of this current, you are able to maintain figure A, B, and C. A, B means phase A current, phase B current, phase C current. Phase A supply current, phase B supply current, phase C supply current. How we are able to maintain this one? Due to converter A current, converter B current, converter C current. And what condition? When we have a unbalancing in load. Our load is unbalanced. In two phase, we have a load. Third phase is load is 0. Means we have created 33% unbalancing. Any question? Maybe you can tell me some problem with that. Same thing also you can observe from dynamics cases. For dynamics, we can use DSO to record those results. And during that time, also you can see condition of DC bus voltage. See, load is unbalanced, figure B, bus supply is balanced sinusoidal. This is the load balancing phenomena. Also you can see during these conditions, if load is unbalanced, what is nature of supply current, compensating current, and load current with DC bus voltage. Our DC bus voltage not going to shoot over, or maybe not going to jump here and there. Near to reference, maybe this one is settled only. During these conditions, also you can see PCC voltage. So here we have plotted PCC voltage with respect to compensating current phase A, phase B, phase C. Also you can see if load is balanced, since load is switching type of load, that time how much neutral current we are going to observe, that neutral current may be equal to load current. Okay. How we can compensate? We put on transformer, and after transformer, load neutral current and transformer neutral current going to become equal and opposite, and supply side going to become 0. After that, at a moment you are going to observe unbalancing in load, then your transformer, your load neutral current is going to increase how much? 73% extra from load current. Your load neutral current is going to increase from 1.73 into IL. Load neutral current is going to increase how much? 1.73 into IL. Okay, those you can compensate. Also you can see how we can maintain 0 voltage regulation mode. See here, in PFC mode, at no load condition, how much voltage we have taken? 160 volt. And 6 ampere we have put loading. Voltage going to reduce up to, voltage have gone up to 153 volt. That one we want to maintain 160. In this way, we have maintained 160. By current how much? 10.3 ampere. In 4 ampere extra current we need to compensate the 6-7 volt. This is experimental case only. Maybe field application, maybe In the practical application, that will maybe also decrease. Or in experimental work, this much, the 3-4 ampere kind we need to compensate the 6 to 7 volt. Okay. Here 10.38. Previously how much? 6.53. Okay, 4 ampere. How much to compensate? They are about 7 volt. Okay. Then in that time also you can see nature of compensating power. Nature of compensating power. Here you can see capacitor going to supply how much voltage, how much current, how much power, 2.58 leading. At same time, also you can see nature of supply current and you can see supply power factor. Supply power factor how much? 0.72 dpm leading. Okay. Means we are going to have a leading power factor. That is point. Same way we can see condition of DC VT terminal voltage and all these component, load, supply, and AC voltage. So whatever we have discussed on basic control only, using that one we have maintained. We have seen the result of PFC mode and ZPR mode. And people can also work in this area, and they can apply these algorithms or maybe other algorithms also in any distributed power generation system, wind, solar, hydro, whatever there, and or any other area also. So how we can develop this system in our laboratory? For that one, we need processor. So maybe we can use any D-space processor, any DSP processor, or any microcontrollers. But in that, we should have ADC, DAC, digital I/O, PWM port. Also, we should have facility to write the code also, or maybe we can write the. What we can write? We can dump the MATLAB simulations. In our lab, we have also we need sensor card also, voltage sensor, current sensor. Also, we need some amplification circuit. So in our laboratory, we have our laboratory means in the year 2013-14. That time, 5 years before, we have this sensor card. Also, we have, but now we have improved our setup. Previously, we have one CT and PT. We have a voltage transformer, small voltage transformer. We have sensor voltage. Okay, and also we have one local made CT. Also, suppose we have one leg na, at a time, 2 IGBT should not on with at a time 2 IGBT should not on with DC bus voltage. Means suppose we are going to change first IGBT to upper IGBT to lower IGBT, change over time. Change over time, chances are short circuit are there. Chances are short circuit is there with DC bus voltage. If same leg both IGBT are on, that becomes short circuit and DC bus also going to short. For that condition, we need to create the one dead band. Dead band how much? Not more than 2 to 5 microsecond between same leg 2 IGBT. If one IGBT on, and we are going to change the one IGBT on to off and second one off to on. At that time, we should maintain at least 2 to 5 microsecond dead time. How we can maintain? For that one, we have used IC 7400. With the help of this one, we have designed the circuit. Okay. This is our detailed circuit, and with the help of this one, we have maintained the 2 to 5 microsecond delay time between two IGBTs. This is our voltage source kind of very low cost converter only, 3 to 4,000, 5,000. So this is our low cost converter. With the help of this one, we have generated the required. This capacitor going to work as a this voltage source converter going to work as a capacitor with the help of this driver circuit. But initial stage in the year 2013-14, we have worked in this converter only. Or maybe if we are going to develop some high rating system now, the first we can run with low cost equipment only, so that if some problem is there, they will fail, no problem. We can repair also. In this case, driver require how much voltage? Plus minus 12 volt. Okay. And this is 6 leg also we need. This is RC filter. You can see in initial stage how we have designed this RC filter. This is the resistance, this is the capacitor. In per phase, depending upon requirement, you can connect the capacitors per phase basis. Second device is DVR. After that, we will go applications. Okay? If some problem is there, question is there, you can ask something. Any question? Okay. Now we are going to start second device. With the help of this one, you are going to compensate the voltage-based power quality problem. Whatever we have discussed, that one only used for the compensation of current-based power quality problem. In this case, what are the voltage-based power quality problem? First, you can consider voltage sag, voltage swell, balancing, notching, flickering, then distortion, then others what we can say. For others, you can read books also. So many books are there. In this case, again, we have many topology of voltage source converter. That converter work as a DVR, dynamic voltage restorer. So maybe you can use this device in 3-phase system, or maybe 3-phase 4-phase system. In case of 3-phase 3-phase system, you can use 3-leg converter. In case of 3-phase 3-phase with speed capacitor, you can speed the capacitor. But problem is we need double rated DC link voltage. Also, we can use 4-leg converters. Also, we can use 3 single-phase converters. Also, we can use 3-phase 4-wire system, 4-leg converter, 3-phase 3-wire system, 4-leg converter. Also, maybe we can use 3-phase 4-wire system with speed capacitor, matrix converter. Also, we can use multi-wire converter. Also, we can use depend upon the applications. Generally, this is the maybe you can say if we are going to see if we have a voltage stabilizer, UPS, and DVR. So maybe you can say this is the one member of this category. Voltage stabilizer also going to work for stabilizing the voltage. This one is going to maintain the bus voltage at industrial application or maybe mini power application. EPS also going to maintain the required voltage with less value of distortion. So maybe also you can say line interactive UPS known as the DVR also. But also we can see operating times. So maybe somebody can find out the answer of this one. What is the difference between UPS, DVR, and voltage stabilizer? Again, this is one topology of 3-phase 3-wire system. The whole system maybe you can design based on the DC link, or maybe you can design based on the energy storage system. With the help of energy storage system, you are going to reduce this converter ratings. But we need extra cost of DC bus energy system. But in that case, rating voltage source converter rating going to reduce because we are going to we are going to inject the required voltage in phase with PCC voltage. A PCC maybe voltage both are in same phase, so we are going to inject compensating voltage in phase with PCC voltage. Okay. So we have 3 mode of operation. One is the see here. Okay, first topology we will see. Second topology there, maybe DC link voltage you can use. In case of DC link voltage, our compensating voltage coordinated with line current. Here converter is going to increase, but we have reduced the cost of the DC bus voltage. We don't require any extra source. Only DC link voltage you can maintain by line to line. DC link voltage you can maintain by PCC only. Okay. In this case, we have reduced the DC bus cost. We don't require any extra energy source. With the help of supply, you can maintain the capacitor voltage. In this case, you can use self-supporting DC bus voltage. In this case, you can use self-supported DC bus. Okay. What problem is needs some higher rated converter. After that, also we should have one interface inductor, injection transformers, 1, 2, 3. Three injection transformers because we have 3 base, 3 inductors. Also, we need capacitor also, so that we can block the converter distortion due to switching. Whatever distortion you are going to observe in converter output voltage, that one we want to block. Okay. Again, here rating of this DC bus voltage depend upon the converter side transformer voltage. In this case, rating of DC bus voltage depend upon converter side AC voltage. Based on that one, you can design the DC bus voltage. And primary side, line side converter, line side transformer voltage depend upon the required compensation. How much compensation we want. Okay. Line side voltage depend upon the required compensation. Okay. Then you have a one maybe linear load you can consider here, because our supply is distorted and balanced. Voltage in that case, assume that load is balanced, sinusoidal. If unbalanced, in that case, we need to calculate the fundamental positive component. With the help of that one, you can find out the template to generate the gate signal. Okay. Third case, maybe we have 4 leg. 4 leg means energy source. So 3 wire with 4 leg converters you can use. 3 wire system with 4 leg. The fourth wire you can make common. You don't connect anywhere. Also, you can design 3 single phase converter. Mean independent control of our 3 phases. You can make control. Design based on the 3 leg with energy source, and you can put one transformers delta star. Speed capacitor with energy source means you can use any solar, wind, hydro, whatever you have a distributed power generation. Their energy sources are there. Based on that one, also you can supply here and you can get the required compensation. Also, you can use matrix converters and that PCC voltage and load voltage you can maintain. Also, you can use multi-level converter, and maybe we have rectifier supported DVR also we can design. One case, maybe you can maintain DC bus voltage from PCC. Second case, maybe with the help of rectifier you can charge the capacitor. With the help of rectifier, you can give the supply to capacitor. Then you can filter out the ripple component, and filtered by row of DC bus voltage you can give to multi-level converter. After that, depend upon your requirement, you can generate the compensating voltage. Now we should compare all the topology. You can compare based on the whatever literature are there. You can see here we have basically 3 mode of operation. One is a preset, second is the in-phase compensation, third one is the energy optimal compensation. Okay, whatever I have told in phase, quadrature and optimal. In phase, quadrature and any angle between 0 to 90. Based on that one, we can decide the rating of the voltage source converter. Just you can see the diagrams. In first case, some alpha angle there. Second case, compensating voltage, VD and VS both are in same phase. Third case, with line current, compensating voltage VD is going to maintain 90 degree. With the line current, compensating voltage is going to create 90 degree angle. Okay. So the first case, to the control you can make. Second case, change the energy source. You can put some active energy source. Third case, with the help of simple capacitor, you can compensate the whatever voltage-based power quality over there. Again, in this case, we have many topology, many controllers. So maybe you can use time-based algorithm or frequency-based algorithm. Maybe classical, transform, adaptive, anything we can use here. So here, basically, these are the classical type control. We find out the required load and reference current. The first you can find out the fundamental voltage minus DC bus voltage, output of DC bus voltage into in-phase template plus output of AC bus PI into quadrature template for phase A. Phase B fundamental voltage minus output of DC bus voltage into phase B in phase template plus VT into quadrature phase B template. In that way, you can generate the required reference voltage. At that reference voltage, you can compare the actual voltage. You have a gauge signal. That gauge signal you can give respective phase first IGBT, and after passing through the knot, you can give lower IGBT. Again, with transform base, you can use whatever clock and power transformers are there. Based on that one, you can design the controllers. Adaptive control, any type of adaptive control, maybe observer, maybe that PLL, maybe also you can say here any LMS control, anything you can use to generate the required gate signals. Frequency domain also, maybe you can use any FFT, DFT, and DFFT, wavelet, D and D, cosine T and D sin T, any method we can use. Okay. So in this case, what are the possibility? Possibility there you can design the topology. Second case, you can design the controllers. Third case, you can design using MATLAB or maybe any other software. Also, you can design hardware. Next possibility are there. You can tune the value of KPK controller using some subcomputer based techniques. Okay. These are possibility for doing any such work in this area. This is our diagram. Whatever diagram we have tested in our laboratory, we have a setup of DVR. You can see we have one critical and sensitive load. Generally, we have considered RL load only. That we have assumed that require only constant PCC voltage. Require constant PCC voltage. And we have RC filter. Before that, we have a source impedance, interface transformers, interface inductors, voltage source converter, DC bus voltage. Then we have PW generators. You can generate required gate signals. Again, based on the how we can decide the rating of induction transformers. The first you can find out the how much voltage we want to inject. First we can find out how much voltage we want to inject. That voltage into per phase we want to find out 3 phase rating na. So we per phase also you can calculate 3 into that phase voltage into line current, because we are going to connect transformer in series with line. So whatever line current are there, for same rating you can design the voltage source converter. You can design the interface transformers. But we should know how much voltage we want to compensate. In this way, you can design how we can design the voltage source converter and DC link capacitor. So, root 3, how much voltage we want to compensate, the compensating current. Based on this formula, you can design. Here, generally, current rating is chosen equal to load current only. Whatever load country there, load country there. Based on that one, as equal to that one, you can design the current rating of converter. Because secondary side also series with line only. But again, we are going to buck or boost the secondary side voltage. Generally, we are going to reduce the voltage. So then we have a less value of DC bus voltage. If voltage we have reduced, the current is going to increase. That is also point out there. How much DC we should maintain? We should maintain at least more than 2 root 2 into converter voltage. 2 root 2 into converter side voltage. This much DC we should maintain. With converter side, whatever voltage we have assumed that, suppose we want to compensate 100 volt, and we have due to reduce for reducing listening, assume that converter side we have assumed that 50 volt. So 50 into 2 into root 2. That much you can maintain. If we have taken 1:2 ratio, if we have taken 1:1 ratio, 100 by 100, 100 into 2 root 2. That depend upon the means whatever converter voltage you have taken, converter side voltage you have taken, means transformer converter side voltage. We have transformer 2 winding, na primary side depend upon the line. Whatever voltage you want to compensate. Secondary side you can reduce the voltage. Why we want to reduce? Because we want to reduce the DC bus voltage. Okay. Handling the less DC voltage is somewhat easy compared to high value of DC bus voltage. Okay. So based on this formula, we can decide the rating of DC bus capacitor, DC bus voltage. DC bus capacitor, how we can design? Again, we can use 1/2 CV square V injection IL into VT. IL into delta T. Again, I will tell how we can decide the capacitor value 1/2 CV square energy. This is the DC side, na? Equal to AC side how much? 3 V converter voltage, I converter current, T means recovery time. Again 3 phase. Again you can say some factor also, because in dynamic condition we are not going to. Okay, then our load is fixed only. So we have maybe they have not taken any factors maybe. Okay, so means you can take with the help of this one you can calculate the value of converter DC bus voltage, DC bus capacitance you can say. Whatever you have VDC and VDC delta VDC, whatever DC link voltage you have taken, that one minus whatever by calculation you are getting DC bus voltage. That means suppose calculation we are getting 180, but round figure is 200, na? So 200 square minus 180 square. How we can decide interfacing inductor and repeat filters? Interfacing inductor, you can use this formula K into square root 3/2 VDC divided by 6 star A F del I. How we can decide ripple filter component, capacitor and resistor. The capacitor we can decide by 1/2 pi F RC. Based on this one, you can decide the value of capacitors. You can use any type of controller, depend upon whatever you want to select, and depend upon the application performance. Maybe you can take any PLL, you can take any observer, those things you can take, and try to compensate distortion, unbalancing, sway, shake. Here we have compensated, and we have recommended means first one ATD PLL. Only it's going to compensate voltage second swell, urban distortion we are not able to compensate. Second one is all four components we can take. Third one, all 4 functions we can take. Fourth one also we can take all 4 functions. Means if we are able to calculate positive sequence component, then you are going to compensate all 4 problems. If we are going to compensate only, if we are going to create only fundamental component, by fundamental only you want to compensate 2 problems only, voltage second swell. This is also one theory. Okay. Means with the help of fundamental, only you want to compensate second one. With the help of positive sequence fundamental, you are going to compensate all 4 problems. All 4 means other problem also. This is one basic diagram. How we can generate the gate signal. This is also maybe okay. How we can generate gate signal? In this case, first you can set the DC bus voltage and compare. Put PI controller, tune the value of KPKI. You have a loss component. You can consider that one. Set the source voltage. No, here you can sense load voltage. Okay. Okay, so sense the load voltage, convert ABC DQ. After conversion, you put LPR filter. You can find the perfect DC value. Then separate from output of PI controller, AC bus. Second case, you have a reactive component. That value you can separate from load reactive means you can separate from AC bus PI control output. Both you can add. After adding, you have a VD star and VQ star. And then DQ convert to ABC, you have a VLA star, VLB star, VLC star. Compare with actual value of load voltage, then you have an error. That error you can pass to PI controller. After passing PI controller, you can compare with tabular wave, carrier based signal. Maybe carrier based signal with selective frequency. So maybe we can take what we can take. We can take tabular wave. After comparing whatever signal is coming, you can give respective phase first IGBT. After passing through not, you can go lower IGBT. In that way, you can generate 6 gating signals. Again, in conversion of ABC to alpha, ABC to DQ and DQ to ABC, also we need information of sin theta cos theta. Here, current you can assume that as a reference. So with that sense value of load current, you can give to PLL, and after giving PLL, you can generate sin theta cos theta. Although sin theta cos theta, you can give conversion of ABC to DQ and DQ to ABC. Okay. Conversion of ABC to DQ and DQ to ABC conversion, you can see information of sin theta cos theta. Okay. And whatever voltage you want to maintain, that voltage you can put as a VL star. Suppose you want to maintain some value of voltage, 5 volt, 10 volt. Suppose we have a DC bus, we have line to line 50 volt, line to line 60 volt. Okay, na? Suppose we have line to line 60 volt. So based on that one, you can find out the amplitude. Okay, then compare. Or you can put reference as a positive. Then you have PI controllers, output, add with load reactive. You have a VQ star. Then you have a conversion of DNQ to ABC. In that way, you can design controllers. Also, you can read many people also are there. We have also written some papers in the case of DVR also. Those also you can see. Whatever I have to, there's one basic control only. How now you can see after compensation, whatever performance we are going to observe. Then you have a supply voltage. In supply voltage, you have so many columns here. Normal voltage, set, normal voltage, swell, normal voltage, distortion, unbalancing. All 4 columns we have created here. These are the output voltage from converters: VCA, VCB, VCC. Load voltage, how much? We are able to maintain sinusoidal rated value of load voltage after compensation. See the load current also. Load current we have taken linear load only, linear inductive loads. At that time, see the condition of the VT, terminal voltage. Terminal voltage going to maintain near to rated voltage, near to required voltage, not rated. DC bus voltage, here in this case, we have maintained the DC bus voltage near to 300. Okay. See here, time response. How we can say our controller is good or bad? That is main thing. So now you can select particular column and calculate the response time. That after this much time, our system is going to respond. Here we can see after how much cycle? 0.9 at 0.92, our converter is going to react. We are going to get the response after 0.93. In that way, you can create your contribution. Means we should show some contribution also, na? So we can create the particular column, or you can show the contribution in terms of controller, maybe in terms of that response time, maybe in terms of that setting time, rise time, fall time, those cases. So in this case, also we have done some work. Here we can tune the value of KPI using optimization techniques. Here we have used the PSO, MPPSO, TACPSO, AGPSO for tuning up KPI. All those cases we have found out the number of iterations, value of KPI in case of BC bus, AC bus, and value of cost functions. Cost function we have taken whatever standard error function are there. We have taken. Okay. So you can see PSO that had taken how much? 7th iteration, MPPSO 7, TACPSO 10, AGPSO 6, and that. Mean what we are going to discuss, that is the based on the PSO only. Then again we have find out the using PSO what time advantage we have got. Again, this is the one component of contribution. In papers we will show contribution also. So here we have shown what is the peak magnitude, rise time, settling time. Using PSO, MPPSO, what are method are there those based on that. We have find out the percentage, peak magnitude in percentage, rise time and settling time, those values. Also we can see how we have calculated those values, you can see. So with the help of this graph. DC link voltage or maybe AC link voltage, AC bus voltage, for any condition you can create these points. For any case, we can create these phenomena. Okay. Then, since we have developed this whole system availability also, then we have used DSO processor, Fluke and that DSO. Then also we have used Microgrids box to implement this algorithm. The whole means that performance. We have compensated voltage near to voltage distortion. How much? Near to 1 to 2% only. This is our setup. This setup we have developed in our laboratory. This is a DVR setup. In this setup, you can see how we can create the non-ideality in supply voltage, because we don't have such well now. Our supply voltage normal only. In that case, maybe you can put to create the set. You can switch on the some high value inductor. Means within 5 to 10 seconds only. Because we don't want 1 hour, 2 hour. Within just you can switch on an hour. Also you can to create the distortion. Also you can connect one rectifier parallel to PCC parallel to supply source, and output of rectifier you can connect to RC load. In the output of rectifier, maybe you connect RC load, RL load, or maybe mixed load also. Because you want to maintain at least 10 to 15 volt, or maybe near to 10% distortion in PCC voltage. What are field value there? Okay. Then how we can create swell? For that one, maybe you can connect capacitors. How we can create unbalancing? To create the unbalancing, you connect one high value of resistive load between two phases. To connect the unbalancing, you can connect high value of resistance between two lines, and you can put some kind you can flow from there. So your voltage going to dip. In that, if two phases voltage going to dip, means you have automatically you have an unbalancing of three phases. These are the interface inductor. Whatever inductor I have told you, that inductor are there. This is the inductor 20 ampere, and 0 to 20 millihenry we can change by taping only. These are the interface transformers. In these transformers, we need 3 transformers. At least we need 3 transformers. We have taken 4 kVA each rating, and we have put both sides taping 0, 20 volt, 50 volt, 70 volt, 90 volt, 110 volt, 150 volt, 170 volt, 180 volt, 200 volt, so that based on the requirement we can put turns ratio. We can decide the rating of the DC bus voltage. After this is the RC filter. Also in the sensing circuit, we have designed the one sensors we have designed. LEM sensor we have used. Processor microlab box we have connected with this means what we can say this PC. This is our 25 kVA converter 4 leg, and this is a plug converter, plug multimeter, power quantizer. These are DSO. Four setup we have developed. After developing the setup, we have compensated whatever problem we have created or we have got from supply. And differential probe we have used to to capture the performance of the system. Also, we have CAN probe also we have used to capture the dynamic performance of DVR. And this is the DVR, and the right side away that is a shunt filter. In our laboratory we have a both setup, shunt and series. Also, we can make UPQC also. These are the detailed diagrams. This is a microlab box. Then we have a sensor circuit. Then we have converters, voltage sensor circuit and current sensor circuit. These are the interfacing circuit. We can interface power circuit to control circuit. Okay, that is requirement. So low control circuit we have a low power, and power circuit we have high power. Then we can make optical isolation. So with here 6 and 136, you can get the isolation. Also you can make amplification. We can amplify the whatever gas signal we are getting from microlab box to requirement of converter. So with the help of this whole circuit, we can amplify. Our amplification we have 2N2222 transistors, and based on the requirement of driver, we have designed the value of 4.7 1 kilo ohm, and also based on the ADC, we have put the ADC after avoiding the condition of ADC current, we have put the 1000 ohm resistance. Okay. Also, you can see RC filter. So many capacitors we need to develop the whole setup. They are transformers, inductor. Below we have a 4 kVA inductor. Above that we have a below that one we have below figure is the 4 kVA transformer, interface transformers. Above the 20 milliampere, 20 milli Henry and 20 ampere inductor. Up to 20 ampere we can go. We have taken somewhat higher capacity. These are the whole data. 300 estimation we have taken. Interface transformer, interface inductor, annual we can take, depend on our choice. Injection transformers, depend on calculation. We have a 12 kVA capacity we have. With up to 12 kVA, we can test the system. This is a conclusion. We have compensated all water power particle we have used, and we have tested somewhat 10 to 20 algorithms till now. The differences. Now, some more are there. Next case, how we can apply these system for distributed power generation. If some question is there, that you still implementation something. Now next section is application of this shunt filter or series filter in distributed power generation. We have taken wind here. Wind we have taken. In wind farm, we want to apply these systems. Just you can see circuit, then I will explain it. First, you can see the component of the all the component of the circuit. Okay. So you can see the right side first. Assume that we don't have power supply anywhere. Suppose we have a remote area in that we don't have power supply. To get the power supply, we need transmission line, distribution line, substations, service line, those things we need. Suppose I want only 5 kilowatt power, 10 kilowatt power, I mean 50 kilowatt power, 5 kilowatt power, 5, 10, 20, any value. And a remote area maybe 500, maybe 50 kilometers away from Earth. Maybe you have some hill area. In that place, we don't have anything there. But we have a wind farm, wind there. By wind, you can put one in smart setup and connect that wind power to induction generator. Me power converter, you can show the induction generator or maybe synchronous generator. Here we have both system. I will discuss about something the induction, and after that I will discuss about something about the synchronous generator, me PMHC. So first you can take wind turbine, take the induction motor machine, and output of induction machine connect to it. Hello? हाँ ठीक है, हाँ 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 ठीक है, भेज दूंगा अभी तुम, ठीक अभी मतलब एक आधे घंटे बाद चलेगा, कल को आधे घंटे मैं 2 बजे पहले कर दूंगा, ठीक है, हाँ ठीक। Hello? Now you can see. After that, we have a maybe 3 wire load, maybe 4 wire load. Assume that we have a 4 wire load. Whatever we have discussed, topology of distate same thing. And now we want to utilize 100% power, na? Because in that place we have less power only. So I want to utilize 100% power. We don't make any loss. We don't want to make any losses there. So for that one, reactive power you can generate by this converter. At local end, you can get the reactive power. Also, you can generate that neutral current compensating power. First, most requirement is how we can get problem here. See, turbine has some torque, TM. Turbine torque with, you can say some name you can give, mechanical torque. Machine also have some torque, load also have some torque. It must turbine torque equal to machine torque. Okay? And load torque. All 3 torque are equal. In that case, no problem. Our system will run smooth only. Okay? Second case, suppose turbine torque and machine torque both are equal, but load is going to reduce. So what type of problem we are going to observe? If load is going to reduce means we have a rated generation. Suppose 3.7 kilowatt. We have rated generation and rated power going to generate are going to fit the load. But load not going to accept. Load is going to accept only 2 kilowatt. What about extra 1 kilowatt? Extra 1 kilowatt, maybe you can connect one extra load also, dump load also you can connect, all load or something, all load you can connect, or maybe extra load you can give to some other source, some other load. Okay, but if we are going to connect this with a battery based system, whatever we have discussed only DC bus voltage. In DC bus, we have connected here one energy source. So first of energy source is, if load is going to reduce, what type of you are going to observe? We have extra power, our voltage going to boost, frequency also going to increase. Second case, if load is going to increase, then our frequency is going to dip and load also going to, frequency is going to dip and voltage also going to dip. To solve voltage frequency problem, we can connect some extra systems. But using this state-com, using this shunt filter, we have extra facility also. If load is going to vary, whatever extra power we have, that extra power you can store in battery also. And when we have some less generation, that extra that active power also you can take support from this battery. Okay, so what type of function we are going to observe? We have many functions. One is that you can compensate harmonics, reactive power, unbalancing, neutral current, along with voltage and frequency. You can maintain the required voltage and frequency using battery-based systems. Okay, so battery, generally we are going to use battery in case of wind farm only. Because wind is fluctuating only. Always wind is going to change here and there. Very less fluctuation only. But there, whatever due to that, whatever fluctuation we are going to see in the power generation, that one, to take care of that one, we need battery. Okay. Okay, now means with the help of this one, we can solve the voltage frequency based problem also. And whatever function are there, delta star transformer, that one okay, no problem. Whatever problem we have observed, whatever problem is, whatever problem we have observed due to that fourth problem is due to neutral current. Na? That problem you can solve using this delta star transformer. Secondary side you can make delta, primary side you can make star, and that transformer is going to support the extra anti-phase current, anti-phase of the load current. Due to that one, we don't have any neutral current in supply side. Neutral, we supply side current, supply side neutral is going to compensate. Okay? For that one, again we need some controllers. With the help of that controller, you can design the gate signals and you can give the gate signals. This is a basic theory. And also, second case. Next case, support turbine power is less. Okay? Generator will produce less power only. Then, whatever we have stored power in battery, na, and load demand is high. Whatever demand is there, rated demand, rated demand, load is going to demand rated power only. So whatever rated demand is there, na, that one you can fulfill by the extra energy source. Here, 3-4 functions are there. You can see this is our basic equation for basic governing equation for operation of generators. So J d omega m by dt into Tm minus Te. Basically, this one you can observe, you can see from any diagram book. The main problem associated with induction generator is main problem associated with induction generator in standalone mode of operation is voltage and frequency fluctuation under application of load on it. Due to load, we have a voltage frequency fluctuations. With those you can take care. You can understand by these two equations. Tm is a machine torque, that turbine torque, mechanical torque. T electrical torque. TL is a load torque. So machine torque minus means turbine torque, Tm minus T means mechanical torque minus electrical torque equal to how much? J d omega by dt. But electrical torque minus load torque depend upon the H into d omega E by dt. One is mechanical speed, one is electrical speed. J is the moment of inertia of turbine. H is the inertia constant of generator. Omega m is the rotor mechanical speed. Omega E is the rotor electrical speed. T, TL, Tm. Tm, Te, TL. Tm is the mechanical torque. TL is the load torque. T is the electrical torque. From this, it is clear that torque equilibrium is required for constant frequency and voltage operation. Whatever equation we have seen, from that one it is clear that torque equilibrium is required for constant frequency and voltage operation. Voltage operation of the generator. Okay. For some states such as increase wind velocity, if turbine Tm is more than generator. Again, at particular condition, assume that increase in wind speed. If turbine torque is more than generator electromagnetic torque, the effect is what type of effect you are going to observe? Effect is erosion oscillation will directly increase the frequency of the system. Vice versa also. At particular extent, wind velocity, suppose wind velocity increase some higher value, not very high value, very small value, 8 to 8.5 meter per second, or 8 to 9 meter per second. If turbine torque Tm is more than generator electromagnetic torque, if turbine torque Tm is more than generator electromagnetic torque, then effect in the rotor acceleration, rotor going to accelerate, which directly increases the frequency of the system, and also if decrease, also that one also going to decrease. If disturbance occurs from load side, like load torque more than generator electromagnetic torque, load torque more than generator torque, then get the deacceleration of frequency is going to down. The voltage and frequency are directly related to the voltage generated equation. Therefore, due to frequency fluctuation, voltage fluctuation also start. Voltage frequency are directly related to voltage generated equation. Therefore, due to frequency fluctuations, voltage fluctuations also start. Actually, load torque is not under that control of utility. With load torque, we cannot control. Load torque is independent only. Load torque is not under that control of utility. Moreover, its nature is variable. Anytime we can switch on the fan, anytime switch on the some heavy load, maybe anytime you can switch on the any heavy small machine on or off. With load is not means load is not that in control of the generator. Generator is some other place, no? Maybe 1 kilometer, 2 kilometer away. So with that generator, if we have heavy load, generator going to shut down also no problem. But we don't have a direct control. Generator is going to supply power, whatever power is he getting from source. Maybe wind, maybe hydro, maybe solar. For that one, again we can use some control techniques. How we can get gas signal? So previously we have set the DC bus voltage, and we have compared with reference value PI controller. Also we have find out the VT, reference VT. Then we have PI output. That output we have given to load reactive component. Output of this DC bus voltage we have given to P component. In this case, in place of DC link voltage, you can put reference frequency. Here we are going to put 50 Hz reference frequency, and we have changed the what frequency are there. I want to maintain 50 Hz. I want to maintain this much voltage. I want to maintain rated voltage with 50 Hz. So based on this one, based on this formula, again you can tune the value of KPKI. If we are going to get minimum constant DC, then you can. Hello? Okay. In this case, in case of wind farm, we need to maintain voltage and frequency. So we can use one voltage loop, one is a frequency loop. Okay. Again, you can use part transformation and inverse part transformation. Simply SRF theory you can use. So you can sense the load current. After sensing load current, convert ABC to DQ. Then you have a D and Q component. You can use LPF. You can filter out. You have every value of D and Q component. With D component, add with output of PI controllers. With Q component, AC bus PI output you can subtract from Q component. You have a ISQ and ISD. Now these D and Q component you can convert to ABC DQ. Then you have ISC star, IRA, IRB, IRC. These are reference current. Compare with actual value. Then you have a error. That error you can give to gate signal. With that, for that one you can get the gas signal, and that gas signal you can give to first respective phase, first IGBT. Same gas signal you can pass on not logic. You can do respective phase lower IGBT. In that way you can generate. Since getting signal, you can switch on your converters. Again, carrier means with the help of carrier signal, you can decide the switching frequency of the converter. Okay. What are voltage? Why we want LPF? Because if we are going to find out the VT, VT how we can find out? Square root of 2 by 3 VSA, VSB, VSC square. Formula is VT equal to square root of 2 by 3. Inside of that one, VSA square, VSB square, VSC square. In this formula, you will get one average value. Second, you are going to get the. Hello? रुकिए मैं भी क्लास पे आता हूँ 12:30. ठीक है 12:30 क्लास आ रहा है. 12:30. Okay, so okay, then whatever you have find out the average value, na, with average value also you will get some oscillating component. To remove the oscillating or ripple component, we need LPM. How we can decide the value of that? Inside of that one, suppose we want pure DC, so maybe you can use 2 pi into frequency of pure DC near to 0 hertz. You can don't take the 0, you can do 5 to 6 hertz. You have 5 to 6, no problem, okay. Because otherwise our LPM will not work. If we are going to put 0 hertz, then you are going to get no output will come. You can take at least 6 to 20 any value you can take, depend upon response. If the response not getting very good, you can decrease 20 to 18, 15, 16, then 10, 12, then you can go up to 5, 6, up to 6 you can go. After 6, means to implement the LPM, so what keep come. You can take 6 to 5, 6 to 20 any value. How we can decide? How we can means design the transformers? You can use this formula. Okay, so here you can see our active power 3.7 kilowatt. How much reactive we want? 2.77. So you can find out the total power, find out the current, then how much maximum neutral current we want, what is the maximum neutral current, load into 1.73, you have 20 ampere. Then based on that one, find out the kV rating of the transformers. So we have got here 5.33 kVA. Okay. So means at worst condition, we have find out the current. Our actual load current is 11 ampere. You can see this formula based on this simple only math only. Simple meaning whatever BTech first year is there. Na, for that one, by using that electrical, basic electrical, we have find out. Then, okay. Also, we have developed the hardware setup of this one. So now you can see how we can develop the wind farm in our laboratory. That is main thing. So for that one, we have used induction motor, two induction motor coupled with different ratings. One we have taken 5 HP, or second we have taken here. In this case, we have taken 4, 5, both are 5 HP, but voltage rating different. One case we have taken 240 volt line to line. Second case we have taken 450 line to line. And that whatever motor, one motor going to work as turbine, second motor work as a generator. The turbine we have connected with VFD, and VFD connected to supply source. And with the help of VFD, we can change the frequency. Any value, 50 to 45, 48, 47, or maybe 50 or 52, any value. After that, whatever voltage, whatever supply can the supply, you can use switch, and you can operate with this whole value, a whole shunt filter. And you are connected node, linear, non-linear nodes. Here we have rectifier, you can see. Also, we have a transformer, 10 kV transformer. With the help of that one, you can make delta star. Delta star. With the help of that one, we can make delta star connections. Other connections also we can make. We have a multi-winding transformer, multi-winding you can say. But 100 volt, we have many winding. So based on that one, you can design the transformers. Okay. So here, with the help of this VFD and this setup, we have developed the wind farm in our laboratory. Again, these are the interface transformers, and back side of battery also we have 400 volt DC battery here. Back side of this converter. Okay. Also, we need to design the sensors here. Main thing is sensor. How we can interface our actual voltage to processors to control decks. Here in this case we have used D-Space1104 processor. So with the help of this calculation, you can see. In case of we have used two LV25P and LV55, two sensors we have used, one current and voltage, and we have find out the R in and R out based on our requirement, whatever design we want. Okay, based on that one, we have find out the input and output voltage, and we have decided means sensor output we want 5 volt, not more than that, and rated value. Because here our ADC are plus minus 10. We have bidirectional ADC. If we have bidirectional ADC, based on that one, we have plus minus 10, 5 volt per rated, no problem. And current how much? Current also we have designed here. Current ratings. We have decided 10 ampere output. Okay. So based on that one, we have decided the rating of the R out. We need to see sensor data sheets. Here are sensor circuit. This one we have developed in our laboratory. Last 3-4 years, whatever we have done, from 2013 to 2014, whatever we have done, those I am showing here. This is our isolation circuit. We are getting a signal from that input. After we have a optical isolators, 6 and 136 IGBT, 6 and 136 IC are there. After that, we have a 5 volt. We need to give 5 volt. We need to give optical isolation, and 15 volt we can give to transistors, because we want to maintain near to 15 volt. The transistor need 14.6 or something. This value we should give up to that. Means our IGBT going to turn on after 13.75 up to 15.6. Between that any value we can give. Also, we have created the isolation and deadband circuit. For that one, first we have tested the whole thing in our that PCB, and that general purpose PCB, and after that, means for that one, to capture that nanosecond, we need some high quality DSO also. So based on that one, we have tested. After means before giving that 25K converter, before that we have put some small converter also. So that if every system, all system will work, then we can go to high end systems. You can see we have created 2.5 microsecond dead time. Extra we have created. We have this circuit. These are our experimental setups. Whatever result we have taken 430 volt, 30 cell, 12 volt each, 7 ampere hour. Our the drive C rate is how much? 7.5 kilowatt. Primer is 5 HP. Generator is 5 HP, but voltage difference is there. One is 440 volt, one is 240 volt. Okay. Exciter we have used 4200 volt ampere excitation capacitors. Okay. And also we have the voltage source converter 1200 volt 50 amperes. Processor, we have already, I have told, we have used that DSP 104. Also we have used some small microcontroller to test the system, to test the dead band and isolation circuit. Okay. And for to get a dead band circuit, we have used IC 774F00 PC. That IC we have used on advancement. These are our recorded result, our laboratory only. Now we can see first we want to test a particular algorithm. Okay, so for that one, first we should find out the internal signal, how it is going to behave. Okay. These are the only power quality only. We have compensated distortion, unbalancing, and also condition of DC voltage. Here battery voltage we can say. Yeah. We have battery voltage fixed value only. So you can see if load is going to battery also going to change something. Compensation voltage also, neutral current also you can see both equal and opposite. Just you can see slide number 102, figure number B third and fourth. Your neutral current, the transform neutral and non-neutral equal and opposite. Due to this one, you are going to get balanced sinusoidal current in balance, zero neutral current in supply side. Also, you have balanced sinusoidal current with load and balance also. First high value, some small value. Also, you can see here you can see power balancing under wind variation. Here you can see this is battery power maybe. Battery power by battery going to charge if load is less. Here the whole result in terms of power quality. We have compensated kind of currents up to 3.1 and voltage up to 0.8. Now 34%. Second setup is based on the PMSG. PMSG means just we have changed some advanced, some means PMSG based generator. Same setup we have used, and wind turbine we have connected. Wind turbine means that one induction motor coupled with that what we can say VFD. In this case, speed is not going to change very fast, means frequency problem going to solve. Only we are going to observe problem due to a voltage dip. Those problems we have solved using controllers. So for that one, we have designed one hybrid order generalized integral based control or voltage source converter to improve the power quality of PMSG in isolation system. Okay. Here we have designed some other controllers and that with help of this one, what we can say. With the help of GJ transformer, we have compensated the neutral current. And transformer neutral and that ripple filter neutral we have made common. Sensor we need only just we have changed the machine only, and we have changed the new connection of transformers. In this case, what we have done, ABC to first we have converted alpha beta. After that, we have refined the alpha beta. Okay, and the alpha beta DQ we have converted. After convert again DQ to ABC, and after that we have a reference current. So in this case, just we have put the frequency low, but frequency low is somewhat ineffective only. Some small variation there, that one we can compensate. And also we have used VT 195 and one sense value of VT, that may be not connected. Three phase voltage we have since calculate the value of VT, then we have a LPF filter, compare PI controller output, subtract from LQF. Then you have a modify value of D and Q. After that we have a DQ to ABC, then we have these things. Also you can see response, load current, load ABC, all three phases, then value of supply, value of all these kind. These are different, these are the internal signal only. Hello? नहीं उसको बोले 2 बजे आए 2 बजे तक हाँ कुछ देखो वो 2 बजे तक आना. Also, you can see dynamic response of under tangent operating condition. Supply voltage, supply current, compensating current, load current behaviors, neutral current equal and opposite, frequency 50 Hz, VT, and speed. This is a constant speed operation only. Then you can see the distortions. That one we have compensated up to 5% or whatever I have told now. That 4.53 supply voltage. Supply current, supply voltage how much? 4.83. Load side how much? 39%. 39% to less than 5% we have compensated. Now you can see dynamic response under tangent operating conditions. Again we have put some tangent. Then also we can see how we are telling you we have done some new control, new algorithm. We should compare with some other algorithm. Here we have compared with some well-developed controller by VSOG. Then we have seen some response in terms of reference as well as the purpose algorithm. In the reference current we have compared for purpose and SOG based systems. Thank you. Any question you can tell? Any question? Thank you, madam, for invitation also. Thank you. Thank you. Thank you.